Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Good morning, everyone. I'm here to introduce Alex Yates. He's finishing his PhD at the University of Washington, working with Oren Etzioni. And he has done a lot of exciting work in the areas of unsupervised or minimally supervised information extraction from the web, and also using unlabeled data to improve the performance of important NLP components such as parsers. So we are happy to have him here today to talk about his latest work. Alex.
Thanks. So hi, everybody. As Christina stated, my name is Alex Yates, and I'm going to talk about today synonym resolution on the web. Before I get into the heart of the talk, though, I want to tell you a little bit about some other projects that I've worked on very briefly during graduate school. Looks like some of my slides being cut off, but hopefully that doesn't become a problem. So the first example I wanted to talk to you about is a data mining application. And this is work that's become part of a startup company called Faircast. You can see the URL at the bottom. You may have heard about it. It's been in the news recently in the New York Times. The idea behind this was that as a consumer, it's very difficult to understand and be comfortable with the market for airline tickets, partly because the prices are volatile. So at any point in time, it's hard to decide, should I wait around to buy a ticket, or should I buy immediately because the price is probably going to go up? So what I did is to take a variety of machine learning techniques, including rule learning and reinforcement learning, to predict an optimal policy for every given time point. Should the consumer buy immediately or wait around to see if the price is going to drop? And using this classifier, I've been able to save, on average, 24% of the ticket price. And that is whenever savings is possible. For some flights, there were no possible savings because the ticket price either stayed flat or rose. And then over all flights, on average, I saved 62% of the optimal level of savings. A second project that I've worked on is in the area of natural language interfaces to appliances. And here, the motivation is pretty clear. If you look at, for example, a microwave, you'll find that there are a limited set of resources available for the actual interface. For example, on this microwave, there are 27 buttons and a small little screen display. And there are a lot of complicated queries that you can issue to appliances, which aren't necessarily obvious from the start. But there's actually a 54-page manual to explain how to use these 27 buttons. So you can imagine that it gets a little bit more complicated than pressing a single button. So what I did was to try and build an interface that was actually a reliable language interface, meaning that the device never goes off and carries out or executes a command which the user didn't intend. So the example that I built was an interface to an answering machine for a telephone. And the device in tests never was actually a reliable interface. It never executed a command that the user didn't intend. In a few examples, in a few cases, around 11%, it did not execute anything and instead asked the user to rephrase the question because it wasn't confident that it knew what the user intended.
Is that using speech?
Well, no. So my prototype was just text-based. The third example I want to give before I get into the heart of the talk is a system that I've called Woodward, after the journalist Bob Woodward. And the reason for that is because it's basically a fact-checking system, just like a good journalist does. So the motivation for this system is that a lot of statistical parsers have poor accuracy on full sentences. The parser that I used for this, the Collins parser, had about a 45% full sentence accuracy on Wall Street Journal sentences. And when I ported it to general web text, the accuracy drops a lot farther. So what I did was to try and check each individual parse to see if I can detect bad parses. And in particular, I looked for examples of pieces of text on the web that were similar to the text found in the sentence, and for which I was very confident that I knew the correct grammatical structure. And using these kinds of tests, when I found examples on the web, I would be able to say that the parse produced by the parser is at least plausible. And if I found no such examples, I could rule the parse out as being implausible. So this is an example of how we can use a large body of text that's completely unlabeled, but we can still leverage that body of text to improve complicated machinery like parsing. On a sample of Trek questions, I was able to reduce parser error by, 67%. And on a data set of Wall Street Journal sentences, I reduced parser error by around 20%. Yeah?
Last question. Won't that kind of classifier be preferred in shorter sentences? Because they should be, easier to parse, or it's harder to make an error there. So if we, filter corpus like that, it will contain most likely, shorter sentences than, normally.
So you're correct, but so the question was whether we could build a classifier that detected bad parses simply by the length of the sentence or features like that. Is that a correct statement? No?
Whatever features are, but at the end probably it will be preferring shorter sentences because they'll be more correct and longer.
That may be true. I don't know actually whether or not the filtered set was, in general, a set of shorter sentences. I do know that it outperformed a baseline that just looked at the length of the sentence.
So I guess the question is, so your filter is picking among multiple parses for a given sentence, or it just looks at the top parse and says, well, I don't have a good parse for this sentence, and knocks it out?
That's actually what the filter does. An alternative way of using it is to look at a ranking of parses and rule them out one by one. I haven't carried out that experiment yet, so I don't know how well that would work. So those are examples of projects I have worked on, but for today I want to focus on information extraction from the web, and in particular synonym resolution. So I'll start by giving you a little bit of background about large-scale information extraction, and then I'll talk about a system that my lab has built at the University of Washington called TextRunner. And then I'll go into my system for synonym resolution on top of TextRunner, and then I'll give you some conclusions in future work. So information extraction is basically the process of taking unstructured text documents and producing some kind of structured representation of the same ideas in the text. And there are two main goals for this process. The first is to make information more accessible to people. Text documents support, for example, searches like keyword searches or perhaps regular expressions. On the other hand, a structured format such as a database supports a lot more complicated queries like aggregation and any of the kinds of things that SQL will give you. A second motivation is that we can hope that the information extracted in a structured way is going to be useful for a machine to process. And because of the structure of the database, for example, a machine could understand it more readily. So a typical information extraction system in a classical setting is given a set of inputs including a list of target relations of interest. So if you're interested in, for example, in companies, you might be given the relation where are these companies headquartered. And then a second set of inputs will be the corpus from which to extract examples of the relation. They're typically also given further inputs like labeled examples of correct extractions or a parse for sentences in the data. And then sometimes domain-dependent information about the relations, such as the types of the arguments or whether or not they're functional, and so on. So in this example, the extraction system should be able to extract that the company EMI is headquartered in Miami from this text. Now, when we go to the web, just because the scale of the data set, there are going to be a bunch of necessary changes to how we do information extraction. Partly because there's a lot more text to leverage, and so there are going to be new advantages to the web, and also partly because there are new challenges. So let me go through some of these. The first advantage is that just because there's going to be so many more sentences on the web, there are going to be a number of very easy to understand sentences. So we should be able to extract stuff using fairly simple techniques. And hopefully we can do away with some of the heavier weight processing like parsing. A second advantage is that we can use the redundancy of the web. There are going to be a number of different authors saying very similar things in different ways. And if we can extract the same fact multiple times, we should be more confident that that fact is correct. A third advantage is that there are existing tools like search engines for giving us information about the web on a large scale, such as hit counts. And then there's information about just about anything you could want to look up. On the flip side, there are a number of new challenges. In particular, if we tried to apply a parser to the whole web, it could take months or even years. So we're going to look at using lighter weight processing. Like in a similar vein, it's going to be harder for the parser to parse the web just because there are these ungrammatical sentences and sentences that have a different distribution from the set that it was trained on. Also, we're not going to be given the same kind of inputs that a traditional information extraction system is given. We're not going to have any labeled examples of extractions for each relation of interest because there are millions of different relations that we're interested in. There's also examples of unreliable information on the web. People say pretty wacky things. And because there are diverse topics on the web, it's hard to tailor our methods to a particular domain. So in response to these challenges and to take advantage of the new advantages of the web, our lab has built this system called TextRunner. And basically, TextRunner is an information extraction system that does away with many of the inputs required by traditional systems. It doesn't take any names of relations at runtime. It doesn't require a parser. And it doesn't require any labeled information. So let me give you an example of how this works. Given a sentence like, eBay was founded by Pierre Omidyar, TextRunner begins by finding noun phrase chunks, which is much faster in general than doing a full parse of the sentence. It then identifies short pieces of text between noun phrase chunks as filler or potential relation material. Then after applying a series of tests to this filler, it'll decide on the fly whether or not to extract it as a relation. And if it passes these tests, I'm not going to explain in detail what those tests are. You can look at the reference I've given you. If it passes these tests, it'll extract the relation whose name is the filler and whose arguments are the noun phrase chunks on either end. So we've run this process on a set of around 150 million web pages and extracted several hundred million extractions, and then indexed the results. And we have a web interface. Currently, our cluster is down, so I can't show you a live demo, but here's a screenshot of a search for the predicate invented. So as you can see, there's some examples of some good extractions, including that Smith invented the margarita and Alexander Graham Bell invented the telephone. There's also some unreliable information. And then there's some examples of just bad extractions. But I also wanted to point out some examples of an interesting phenomena where we have the same fact repeated twice in a slightly different variation. So Smith invented the margarita, and also C. Smith invented the margarita. From the point of view of an user, this is just kind of annoying. You can imagine, for example, on a shopping website, you'll often find the same item listed many times before you get to a new item, and it gets to be a pain to search through them all. So we'd like to be able to collapse these two facts into one. A slightly more problematic example is that we also have Thomas Edison here twice, once labeled as Thomas Edison and once as Edison, with two different facts about him. So now if the user searches for Thomas Edison, they'll never find out that Thomas Edison invented the phonograph because that fact is only extracted for Edison. So again, we'd like to be able to know that Thomas Edison and Edison are actually the same person so we can provide the user more information about him.
So how did digital equipment get the credit for the automatic revolver?
I clipped off the sentences in order to show the extractions in a larger format, but I think I actually don't remember what the sentence was that it was from. If you look on TextRunner, when the demo is actually up and available, you'll see the sentences there, and you can see where it's extracted from. Yeah.
You also have as predicates first invented and invented.
Right.
But without knowing anything, you have no reason to put those in as the same predicate.
Yeah. So the search is actually a keyword-based search right now. So it searches for just invented and any phrase that it finds. There's a way to make it not keyword-based so that it searches for exact phrase. And also there's a way to find synonyms in the predicates. So I'll talk about how I do that in a minute. So what I'm going to talk about for the rest of the talk is basically synonym resolution on top of this set of extractions. And I'll first give you a little bit of background information about the problem of synonym resolution. Then I'll go into some pieces of the solution that I built, including a probabilistic model for how to do this without any labeled text. And then I'll go into some issues about scaling this up to hundreds of millions of extractions. I'll then give you some experiments and some extensions to the basic system. So synonym resolution is the idea is the task of finding synonymous strings in a database. So for example, if we're given two extractions like stood up to President Kennedy, Khrushchev, and confronted JFK, Premier Khrushchev, the system should be able to identify that stood up to and confronted basically mean the same thing. President Kennedy and JFK refer to the same person, and Khrushchev and Premier Khrushchev also refer to the same person, but a different person from JFK. And then finally, it should be able to output a clustering of the strings in this data set into the set of synonymous clusters. So there are a number of existing systems that perform this task, and these basically come in two different varieties. The first is a set of machine learning systems that depend on a lot of labeled examples, and they tend to be very highly accurate, but they have two problems for our setting. One is that they're very computationally expensive. The fastest kind that I've seen in the literature is O of n cubed, and when you try to do that on a set of 100 million extractions, that becomes infeasible. And then, of course, they require labeled data for each different relation of interest. And since we're talking about a set with millions of relations, it's going to be problematic. So the second type of system that people have looked at is a domain-dependent heuristic system. And these typically depend on information about the different relations, such as whether or not they're functional or one-to-one. And very often people work in the citation domain, so they look at co-authorship as a particularly interesting feature of the authored relation. Yeah.
Talk about O n cubed. What is the n?
N is, so there are two different versions, actually. One is the set of extractions, and the other is the set of distinct strings. So typically, for the machine learning systems, they use n, meaning the number of distinct strings. It turns out to be, for at least our data set, because it's ZIF distributed, that those two different n's basically boil down to the same thing.
So where does the cube come from?
The cubed, so the models that they use depend on, there's statistical relational models that depend on using information about the relations that each object participates in a set of relations. Those relations tell you information about other objects that also participate in those relations. So you need to compare objects with one another, relations with one another, and objects with other objects that participate in the same relation. And eventually that gets to be computationally expensive. On a small corpus, the features or the setting in which people operate on a small corpus has features such as they operate in a single domain, and they typically operate on a small known set of relations, and there's typically given an extra set of information about those relations, such as labeled examples, or perhaps information about the argument types, or how close those relations are to being functional. For our setting, though, we're given none of that information. In particular, we're going to operate on many, many domains without knowing the set of relations before we process the set of extractions, and without knowing anything about those relations, and without any labeled training data. So I built a system that I call Resolver, which basically has three key components to it. The first one is a string similarity metric, which is very similar to what people use in basically every type of system for this task. It compares two strings based on the letters they share in common and the sequence of those letters. So I'm not going to talk much about that component. The other two components, there's a way of comparing strings based on the set of extractions about them. I call that the extracted shared property model. And then I've built a clustering algorithm that limits the number of comparisons made between pairs of strings and helps scale this up to the size of 100 million extractions. So the ESP model is a domain-independent model that applies equally well to the problem of clustering pairs of relations and pairs of objects. And it's accurate without any labeled training data. And the other key contribution of Resolver is that I've been able to use it to scale up to 100 million extractions. So let me go now into this probabilistic model. I'll first give you a little bit of terminology and then explain the model using that. Then I'll explain how to calculate that model quickly. And then I'll give you a comparison with the cosine similarity metric, so that hopefully it'll give you a little bit more intuition about how the model behaves. So the key piece of terminology that I'm going to use is the idea of a property. And this is best explained by an example. I call a pair of strings a property, such as discovered relativity. I call that a property of Einstein because the extraction Einstein discovered relativity is in the set of extractions from TextRunner. It would be just as easy to say Einstein discovered is a property of relativity. So the second piece of terminology I'm going to use is the idea of sharing a property. And again, this is pretty intuitive. If two strings are extracted with the same property, then I'll say that they share it. So for instance, Leibniz and Newton share the property invented common calculus. So now I'm going to give you a model of how we can calculate a probability that two strings are synonymous given a set of extractions about each of them. To do that, I want to show you a picture or an abstraction of the information extraction process. So that the text that you don't see there, I'm going to model the process of information extraction as picking balls out of an urn. And the set of balls, for example, for the string United States, I'm going to imagine that there's a set of balls with all the properties of that string in some giant urn, and that we can pick those balls out as we extract information from text. So I call the balls in the urn the set of potential properties that we could extract. And then the set of balls that we've actually selected, I call those the extracted properties. Okay, so as we run TextRunner over a large body of text, we'll select some subset of these balls from the urn. And in particular, because TextRunner is not perfect and because the web doesn't contain all of the properties of the United States, we're going to collect a strict subset. We're not going to get all of the properties of the United States in our extracted subset. So we're going to be interested in comparing two strings, for example, the United States and Canada. So we're going to want to know how many properties do these actually share. In their potential properties, they'll share some subset. In particular, they might share the property that they both joined NAFTA. And then when we extract from these two urns, we should extract some shared properties and then some unshared properties. Since our extraction process isn't perfect, even when all of the properties are shared, we'll extract plenty of unshared properties because we'll extract a shared property from one urn but not from the other. So now the problem for this model is determining a probability that all of the properties in the urns are actually shared, given the number of observed shared properties in the extracted sets. So I've been able to derive an exact expression for that probability if I make a set of assumptions. So the first assumption I make is that each property in the urn is equally likely to be extracted. And that's a little bit counterintuitive because you might imagine that some of the properties appear much more often than others. However, for our data set, over 90% of the properties are actually extracted at most twice, and a vast majority are extracted once. So it's a very good approximation for most of the properties. The second assumption I make is that before we examine the set of extractions for each property, or sorry, for each string, we know nothing about how many properties they share. And then the final assumption that I make is that the properties are actually independent. So each subset of the potential properties is equally likely to be the shared subset as any other subset of the same size. So this is the exact probability expression. I know it doesn't tell you much because you're just looking at this giant formula. The reason I wanted to present it to you, though, is that you can see at the bottom there, it's basically a large number of choose operations. And the model that I presented is a combinatoric model, which basically consists of selecting a number of subsets from larger sets, which, as you know, is mathematically described by the choose operation. So I'm not going to go into the details of this expression. I'll try to give you a bit more intuition about it. Yeah?
So if you threshold this, for Smith and C. Smith, it seems like you would get very large distributions over all the things they co-refer with.
I'm sorry, I'm not sure what you mean.
For Smith and C. Smith, your urns would be rather large and also very diverse.
Right.
Right. So it seems like in this expression, if you just use a strict threshold for making the decision on threshold on co-refer versus non-co-refer, wouldn't that be a problem there? Or?
So I guess there's two parts to the answer. The first is that Smith is actually a very polysemous name. There's a lot of different Smiths. So that's part of the reason why you're going to get a number of different properties in the urn for Smith. And the same is probably true also of C. Smith. So polysemy is a big problem for this model, and it's actually a big problem for synonym resolution in general. And it's not something that I've solved yet. The other part of the answer, though, is that we actually expect very few shared properties in general, even for synonymous pairs. And so there's a pretty low threshold for things being actually synonymous.
So, I mean, to not resolve Smith and C. Smith, I'm sorry,
Go on.
is the right thing to do, actually, because in most contexts, and basically anything other than margaritas, they're not the same person.
Right.
But that points out a problem, which in the sense that you're not resolving synonyms specifically per property or per relation type. So you would like to resolve Smith and C. Smith when you're talking about margaritas, but not when you're talking about anything else.
Yes, right. So you're actually saying you should disambiguate first.
So, do you want to collapse synonyms per relation type, or per based on the other argument, or is it even meaningful to have an abstract notion of synonymy like that applies all the time everywhere?
What I'm saying is that I think the point is that you also need to disambiguate as well as collapse.
Yeah, so it's definitely a big problem, especially for the kind of data that I'm looking at. It's a big problem because it's very sort of diverse data collected over a number of different authors who are going to be talking about slightly different instances of the same name. The clusters that I tend to get are for things that are pretty definitively one thing, such as the United States and U.S., and say that those are probably synonyms in pretty much any context. There may be maybe U.S. is an acronym of some other things, but pretty definitively you can say those are synonyms.
Well, yeah, but even in that case, when if you hit Spanish text, EU and EU in English text is not the same thing, because EU in Spanish text is in fact the United States.
I didn't know that. Our data is actually English. But that's an interesting point. Yeah.
But isn't this problem also exacerbated by the size of the property that you're extracting? Because, so TextRunner, in addition to Smith invented the margarita, presumably it's also extracting Smith invented? Or is it only extracting two-place?
It only does two binary relations right now.
Because I think if you had a variable notion of, if you included more context, your problem of disambiguation would be minimized, would be lessened, because you have a lot more context to base. Your properties are more informative in that case.
Right. So absolutely. For the problem of polysemy, context is obviously very important, and you want to look at, people tend to look at the windows around individual references to them.
By storing only two-place, you've lost that context.
Absolutely. We do store the sentences from which the strings are extracted, so we'd hope to be able to use that for a system that actually tackles polysemy.
Yeah, just a couple of questions about the probabilistic model. So
sure.
I guess the first thing is, if the strings SI and SJ are really synonymous, then don't they have the same number of potential properties? I mean, is the assumption that if they're synonymous, they come from the same urn?
That's a good question. So I've tried a couple of different variations for determining the number of properties in the urn. Obviously, that's an unseen latent variable, and so one setting is to assume that urns are in fact all the same size. Another setting is to assume that they're some multiple of the number of extractions for each particular string, and then there's a couple of different variations on those ideas. The setting that actually seemed to work best in experiments was to assume that they have a multiple of the number of extractions, and I tied that multiple for the experiments that I did. That multiple was the same across all strings, and that actually worked better than assuming some constant number of properties to select from. So that's why I have two different parameters for the number of properties in the urn. So the exact criterion for synonymy that I use is that the number of shared properties between the two strings is the minimum of the number of potential properties in the two urns.
And so this probability is roughly,
I'll show you a graph in a second.
Okay, I'm just wondering, but is it a Bayesian model that we're looking at here, or is it something to do with likelihood ratios, or
this is.
Can you just say a bit more about?
So this top expression here is a is a application of the Bayes rule for the probability that two strings share k extracted properties given the number of shared properties they have in their urns. And this expression here is the exact probability expression for the probability that they have k extracted shared properties. And this comes from basically the urn model and the assumptions that I made. It counts the number of different ways you can have k extractions in a set of, or coming from two different sets of, pi and pj potential properties.
So it's the probability of essentially two identical urns generating the data that you actually observe. Is that right?
Right. Yeah.
It seems also possible that antonyms should have similar sets of properties. Did you see any antonyms in this synonym set that you extracted?
So that actually did come up as a problem for relation merging. And you can think of, for example, is higher in and is lower in. I saw extractions like meat is higher in calories and meat is lower in calories. And then because TextRunner doesn't have then blah, 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 it doesn't know that those are actually two different properties. So in some of the cases that I saw, the resolver merged is higher in and is lower in. One possible way to address that is to look at the number of times and a property is extracted. So meat is higher in calories, tends to be extracted more often than meat is lower in calories. But that's not something that I've completely addressed. The way I address it right now is by looking at string similarity, which is the other component of resolver for comparing two strings. So the expression on this slide is actually basically an O of n cubed algorithm in the number of extractions for a single string. So it's quite expensive to calculate. I've been able to derive a simplified equivalent form that's O of n. And it's possible to reduce that time to calculate the expression using sampling techniques. Now, to give you an idea of how the ESP model behaves, I wanted to compare it with a widely used metric in information retrieval, which is called the cosine similarity metric. And I'm basically going to show you how these two models behave on synthetic data, two strings of 20 and 25 extractions, respectively. And I'm going to vary the number of shared properties between them. So the cosine similarity metric is in blue, and the ESP model is in green. As you can see, the cosine similarity metric goes up linearly with the number of shared properties between two strings. The ESP model, on the other hand, has this hockey stick shape. So you can see that if there's a small number of shared properties between two strings, the ESP model assigns them a probability of close to 0 of being actually synonymous. So it expects that even for very different kinds of strings, there can be a small number of shared properties in the set of extractions, just because even very different strings share a few properties in their urns. After a certain inflection point, the ESP model starts to shoot up rapidly. So for a string of around 20, you get an inflection point around 7. The upshot of that is that the cosine similarity metric, relative to the ESP model, is very overconfident about a pair of strings being similar or being synonymous with a small number of shared properties, and underconfident at a large number of shared properties. Okay, that was an introduction to the ESP model. And I want to talk about how we can scale this process up to a very large data set. Before I get into this, the general process for clustering, this is going to be a clustering problem. Clustering is typically an O of n squared or of O of n squared log n algorithm. But the main bottleneck for synonym resolution is the number of comparisons that need to be made between pairs of strings. And if a naive algorithm would simply compare all strings because they're all potentially synonymous pairs, and in that case, you've already got an O of n squared algorithm because there are O of n squared pairs. So there are two basic methods for cutting down on the number of comparisons you need to make initially. The first is an algorithm that basically makes assumptions about the kind of data you have and then goes off to prove lower bounds, or sorry, better upper bounds about the algorithm. So for example, the merge-purge algorithm by Hernandez and Stolfo assumes that there's a single attribute or a set of attributes in the data such that if you sort on those attributes, all synonymous pairs will be within a small window of one another. So think of last names in a database of people. This model is not going to be appropriate for our setting because there is no such attribute, basically. In fact, there aren't really a large number of attributes that apply to all strings in our data set. So the second type of system is basically a heuristic system that works well in practice. It cuts down on the number of comparisons, but people haven't been able to show a better upper bound for it. So what I'm going to do is show a version of McCollum et al.'s canopy method that actually has a better upper bound. And the algorithm goes like this. In the first step, we build a data structure. Then we use that data structure in the second step to perform comparisons between pairs of strings. And then in the third step, we use those scores that we get from the second step to actually do the merging. And the merging is a greedy bottom-up agglomerative process. It's very similar to standard techniques, so I'm not going to talk much about that. What I want to talk about, though, is the first two steps in which I limit the number of comparisons between strings. So the first step builds an index that points from properties to the sets of strings that it applies to. So for example, invented calculus will be an entry in this index, and it will point to Newton and Leibniz. In the second step, I use that property index to go through all the different properties, and for each property, compare every string that applies to with every other string that it applies to. So, for example, for the property invented calculus, it will compare Newton and Leibniz and calculate a score. So notice in doing that, we've already eliminated comparisons between strings that share no properties. So doing just that eliminates a large number of comparisons, but it doesn't get us to a better bound. The restriction that I've added is that we should only consider properties that aren't too common. So for instance, TextRunner extracts properties sometimes like talk to someone. And as you can imagine, lots of different people have talked to someone. So comparing two strings based on that property alone isn't very helpful because it's very little evidence that those two strings are in fact synonymous. Okay, so again, I'm not going to go through a derivation, but using that algorithm, I've been able to show that we only require O of k comparisons between pairs of strings, where k is the number of extractions in our data set. And this is compared with the naive method, which has an O of n squared algorithm in the number of distinct strings in the data set. So if we assume that the data is if distributed, it's actually O of k. Actually, I should say that O of n is pretty much the same thing as O of k for Zipf distributed data. So it's a big win. O of k is a big win over O of n squared algorithm for large data sets. And again, this speed up is because of two things. We don't compare strings based on, we don't compare strings that share no properties, and we don't compare strings that share only common or high frequency properties. All right, so I've just talked about pieces of my solution for this problem. I now want to go into some experiments about it.
Sorry.
Yeah?
Go back to the previous slide, another one. So maybe I missed this, but this issue of high frequency properties, it's not just an efficiency problem, right? I mean, you can have a lot of, you might think things are synonyms because they share several high frequency properties. I don't know, did you take that into account in your model? I wasn't sure whether you took the frequency of the property into account at all. So
the ESP model as it stands now does not take that into account. I've used versions of it that do, and I'll actually explain this a little bit more in detail later, but basically I've tried, for example, a TF-IDF style weighting of properties in the model, and that actually hurts performance. I've also tried using, for instance, properties, trying to identify properties that are functions, and so should apply to only one or a very small number of strings, and use those as sort of more highly weighted properties. And that can get us a small boost, and I'll talk about that later. But basically, the ESP model tends to perform just as well or better than models that don't take into account the frequency. Yeah, I'll say a little bit more about that.
If you run performance experiments as to see, what is the speed up from that threshold, presumably you get some differences in the accuracy as well.
Yeah, although the threshold that I use is designed so that it only rules out sort of the most ridiculous properties. I use a threshold of 50 in my experiments, and that rules out 0.1% of the properties.
50 instances?
50 extractions of the same property. So in other words, if that property...
9.9% of your properties have less than, like...
So basically, this is a bottom-up clustering algorithm that you're going to run. And the idea is you're going to stop bottom-up clustering at some point. Presumably you'll tell us where. And what's left then, the clusters will correspond to synonym classes.
That's right.
And so that's the reason why you're not using a thing like nearest neighbors or something else like that, because you'd have too many different classes if you were to try and do that sort of top-down clustering.
Right. Yeah.
So could you compare this to canopies, where couldn't you just use the properties as attributes in canopies? Would that be equivalent? Or?
It is. So the reason that this outperforms canopies is basically the second restriction, where I don't consider high frequency properties. Canopies is actually a slightly more general version. If I get rid of this restriction, it's a slightly more general version of what I've presented you, because it'll group things into canopies based on having a certain number of shared properties. But that actually is not enough to get you to a better bound, which is why I've added this other restriction. So the first set of experiments I want to talk to you about is one that measures the accuracy of the system, basically. And I'm going to measure it in terms of precision and recall. I'm pretty sure people here know what that means, so I'm not going to go through this. I've taken a subset of the hundreds of millions of extractions, one of size 2 million extractions, and clustered all the strings that appear at least 25 times using Resolver. And then I've calculated precision and recall on top of that manually. I did this for 4 different methods. The cosine similarity metric I already talked to you about, and the extracted shared property model. And then again, this method that compares strings based on how many letters they share in common. And I call that the string similarity metric. And then finally, the Resolver method combines the second and third method. So for merging objects, there's 2 key points to note. First is that Resolver significantly outperforms both of its components. And second, that the extracted shared property model significantly outperforms the cosine similarity metric. Now, I should point out that all the precision differences are statistically significant. The recall differences, because I did it on a smaller set, and that's just because it's a very painful thing to manually label the entire data set of 2 million. Just a second. The Resolver is statistically significantly different from ESP and cosine similarity metric in recall, but not from the string similarity model. Yeah.
So you manually label the test data?
Right.
So I just wanted to know more how you evaluated this.
Oh, so I did a clustering of, so I took the 2 million extractions, right, and clustered a sampling of that to get basically a comparison set for the recall metric. So the way I decided the clusters was I took a string and looked at all the other strings in the data set that shared a significant string similarity with it. So, for example, if they shared a word with it, and then I also looked at all the strings that shared at least one property, and then from those sets, I picked all the synonyms manually, and so I used that to calculate recall, that manually developed clustering. Then the other.
So when you say synonyms, do you really mean, so there will be sort of exact rephrasing of different entities, like Smith and C. Smith in certain contexts is an exact same entity.
Right.
But when you say synonyms, it could be like margarita, maybe synonym with another kind of drink.
Mm-hmm.
So when you say synonyms, did you include both of them?
No, so I was only interested in
The exact restatement of
yeah, so actually for Smith and C. Smith, I did not cluster those two together because it's not generally true that they're synonyms.
so only, irrespective of the context, things that would
Yeah.
refer to the same entity.
That's right. So for the kinds of examples that I did include were things like U.S. and United States, United Kingdom and UK, Great Britain and Britain, that kind of thing.
Just following on that, what about meronyms, part-whole relationships and things like that? So did your system find them, and how did you evaluate them?
I actually don't think I've seen that as a real problem for my system.
Sometimes I think you find, the chairman of Kodak said such and such, and then Kodak said such and such, right?
Oh, I see.
That sort of thing.
iPod and iPod
Yeah,
Shuffle.
I didn't really see that. Oh, so yeah, some examples where I did see that were with companies. So I saw right. So I remember seeing, for example, like I hate to bring it up, but Google Talk and Google would get clustered, for example.
So what did you just decide to do with those?
So those are all incorrect.
They're incorrect.
Yeah.
Oh,
Okay.
So I did cluster Microsoft and Microsoft Core, or Corp, however you say that, and Google and Google Inc. Where I assigned those as being correct. But so a very similar picture emerges for relation merging. The main difference here is that the extracted shared property model is actually better in F1 score than the string similarity model. But again, the resolver method outperforms both of its components, and the ESP model outperforms the cosine similarity metric.
And do you have a comment as to why the recall is so much less for the relation merging?
Yeah, so part of the reason is that the relation clusters are a lot bigger, and the clustering gets to a certain point where a lot of the decisions are just below threshold, and it decides that it can't merge things together anymore. So after some set of iterations, it'll say it'll just stop and get to a maximum cluster size, and so it never gets to as big of a size on relation merging as it would need to get the full set of clusters. So that's part of the reason. Another reason is that string similarity is a much poorer clue for synonyms in the setting of relations. Basically, morphological variants are really the only good examples.
In both this one and the previous one, string similarity does exceedingly well just on its own, right?
Yeah.
It's recall slow.
It's recall slow. So that should say Mars and Red Planet. What I wanted to show in this calculation is that we can improve on a basic search technique, because we can take synonyms and present more information to users, because now we have more properties per string. So the idea is, as we merge strings like Mars and Red Planet, we'll merge the set of properties for them. And of course, they'll share some properties, so we don't want to double count those. We have to be careful to discount the shared properties. But for the rest of the properties, Mars, for example, will not have all the additional properties from Red Planet that were not shared. So if there's a significant number of unshared properties, will actually improve the amount of information that's available for a search for Mars or a search for red planet. So doing this calculation for Resolver, so I'll just read it from here. It says there are an average of 279 extractions per string before we do any clustering. And there's an average of 564 properties per cluster after we do the clustering. So that's an increase by a factor of over 2 for the number of additional properties that you get per string once you do the clustering. So this is going to be great for a search algorithm. Now if we search for Thomas Edison, we'll get, well, for any particular string, on average we'll get twice as much information out of the search. So here's an example of, oh, sorry, yeah.
But the inverse of that is actually you can look at the unshared properties, right, for uniqueness. You might actually use those differently for, like, ranking, for example, right?
I'm not entirely sure what you mean.
Well, take Red Planet, right? There may be a TV show called Red Planet, right, which has a unique set of properties, right? Yeah, exactly. Mars can be a canning bar. So you can also use, like, the difference of the information, right, to improve results.
That's a good point. And I hadn't really thought about that, partly because, again, I haven't really done a study of the polysemy aspect of the problem. But yeah, up to now, I've just been considering.
The dot operation, right, between them is actually just as interesting.
So here's an example of a search for Hercules, which gives you a couple different spellings of him. And then search for Bill Clinton gives you a bunch of different names for him. And notice some of these names at least don't include the word Bill, so these are going to give you some extra properties. Here's an example for a relation. I don't know if you can read that, but the relation is are eaten by, and it comes up with some synonyms like are rapidly consumed by and are much relished by. So, of course, Resolver and TextRunner aren't exactly perfect. So there are a bunch of different error types that they make. I want to go through some of those. And the first set is basically errors that it inherits from TextRunner. These are extraction errors. So there are a ton of different varieties of these. Here are two examples. It sometimes extracts sentence initial verbs such as learn and discover as objects, and these tend to get merged. It also sometimes extracts compound names like U.S. News and World Report as separate ones, and then they share a lot of properties, so they tend to get merged. A lot of people are working on improving information extraction in TextRunner in particular, so I'm not going to focus on this set of errors. A more interesting set for this talk is this problem of similarity versus identity. And in particular, the ESP model is based on the distributional hypothesis, which says that similar things appear in similar contexts. But we're interested in actually identical things. So here are some examples of very similar things in our data that actually get merged and shouldn't be. And then finally, this thing that you guys have been beating me up for. Yeah, polysemy is a big problem for synonym resolution. It's a source for a lot of our errors. And it's actually something that's overlooked in a lot of different synonym resolution systems. And for me, this is an item of future work. So I want to, though, talk about how we can address that second type of error, the similarity versus identity. And I'm going to go through two extensions to the basic system. First, an example. So Mars and Red Planet. Red Planet has about 70 properties in our data, and there are actually 5 shared properties between Mars and Red Planet. Mars and Neptune. Neptune has actually fewer properties in our data, 69, but more shared properties. So this is basically a problem of noise. And notice that string similarity is not going to help here. So what can we do about this? I've thought of two approaches. The first is, how can we use functional attributes? If we can decide that is named after is actually a function, and we see the extractions that Mars is named after one Roman god, the god of war, and Neptune is named after the god of the sea, we should be able to tell that these two can't be merged. The second technique is based on web hit counts. And I'll go into more detail about that in a minute. So using functions, this relates to the idea of doing the TF-IDF weighting of properties that I talked about a little bit before. So I first tried using functions as positive evidence. You can imagine that functions and one-to-one relations. Take, for example, the relation married. For most people, this is pretty close to a one-to-one relation, not strictly. You can marry more than one person. But seeing that two different strings married the same person is stronger evidence that those two different strings are synonymous than if they shared some random property. Okay, so if we know that some relations are one-to-one, and we can also do the sort of inverse problem for if we had FDR and President Franklin on the right, and we knew that married was functional, or close to functional.
Can you clarify what you mean by functional in this context?
So what I mean is that a relation is functional if for every it's basically the mathematical definition. So if there's two distinct x's, then there have to be two distinct y's. And it's close to functional if the set of y's is almost the same size as the set of x's. Does that make sense? Okay, so the main problem with this, there are two real problems. One is detecting which strings are functional and which are one-to-one. The other problem is just basically sparsity. There's very few shared. It's pretty unusual for a property to be shared between even synonymous strings in our data. So you saw that Mars and Red Planet only shared 5. On top of that, functions in one-to-one relations are rare. So it's very rare to see this kind of evidence in our data. So a second technique that I tried was to use functions as negative evidence. And here, if you know that is named after is functional, and you know that Mars is named after the Roman god of war, and Neptune is named after the Roman god of the sea, you now have evidence, much stronger evidence, that those two are distinct. So I did an experiment using a hand-selected set of functions and relations. Here's a sample on the slide. I tried a variety of techniques for actually detecting one-to-one and functional relations from our data. It turned out to be much trickier than I thought. So for this experiment, I just used a hand-selected set. And I've been able to show basically a small improvement in precision without affecting the recall too much. So the second technique that I tried is based on using web hit counts. And here the idea is that if two strings appear in the same sentence, then it's much more unlikely that they're actually the same or co-referential, if they refer to the same person or object. So in particular, if we search for phrases like X and Y, Mars and Neptune, and find a high hit count, then it's unlikely that those two are actually identical. And hopefully, if we're only considering similar or perhaps identical pairs, they should appear relatively often for similar pairs. If we're looking at totally dissimilar pairs, we'll also get low hit count scores, and it won't help us.
So you're only looking at conjunctions that involve two items here, because you get actually an additional complexity in longer things. You know what I mean? So you get things like Hondas, Toyotas, and other Japanese cars, right?
Right.
Okay. Honda is a Japanese car. Toyota is a Japanese car.
Right. No, but for this, I'm only considering two objects.
I see.
So
For that exact phrase.
yes, I'm actually searching for that exact phrase. And so I compute a score very similar to the PMI score. The main difference is that it squares the top. It's not really important what the score is, but notice that it's significantly different from the score for Mars and Red Planet. And this is on a log scale, so that's several orders of magnitude. And the hit count for Mars and Red Planet is 165 as compared to 13,700 for Mars and Neptune. So you can see it's two orders of magnitude smaller than the score for Mars and Neptune. And so I can draw a threshold between these scores and prevent merges that are above a certain threshold.
You have similarity between two strings, right? But then you have these scores. How do you combine these scores? You do them in sequential or?
I have the similarity and the scores. Oh, so Resolver first gives me a list of merges that I could perform, and then I use these scores to weed out some of those merges. So it's on top of it's a sequential process.
Sequential process.
Yeah. So using this using this, I've been able to show a 7% improvement in precision over Resolver, which is statistically significant, and a 2% improvement in recall. And the other nice aspect of this method is that I don't actually have to supply a hand-selected set of functions. I just have to come up with a threshold, which is easy to do on a development set.
But you also had to provide the query formulations. You did have to know that it was and.
That's true, but that's a one-time thing. I don't have to do that differently for every different data set that I want to do synonym resolution for.
But you might have other formulations that are also expressive of and.
That's true.
That could have what Mark was suggesting, Toyotas. So X, comma, Y, comma, and other. And that would tell you that those are also not identical.
I agree. I think, though, that those tend to be more general across the problem of synonym resolution than identifying particular functions or one-to-one relations, which can vary from different data sets to different data sets. So I hope I've shown you that we can actually use the web and large bodies of text that are unlabeled to improve natural language processing tasks, including, as I've talked about today, synonym resolution. But also, I've done before the Woodward system, which tried to improve parsing. Second, I hope I've shown you that it's possible to build unsupervised models for these complex tasks like synonym resolution. And finally, I've tried to show that you can scale synonym resolution up to the size of the web. There are a bunch of ways to improve Resolver and synonym resolution in general. I've listed some of these. Polysemy is, of course, a big problem. I'm also particularly interested in the idea of mutual recursion, which I'll explain in a second. There's also a bunch of different applications. I've talked about search. That's sort of the motivation for this, but you can imagine things like question answering, leveraging this type of process. So mutual recursion. Up to now, I've been considering object and relation merging as largely independent. But actually, these should be considered dependent on one another. So for instance, if we merged stood up to and confronted in this data set, then we should realize that we actually have a new shared property between President Kennedy and JFK, namely the cluster for stood up to and confronted and Khrushchev. Likewise, if we merge President Kennedy and JFK, we now have a new shared property for stood up to and confronted. Yeah?
Similarly, you could also have a new shared property that were not the similarities between those. Right? Going back to the previous point, which is anything that doesn't, as you collapse those, all the things that don't overlap could actually be considered a new cluster.
All the things that don't overlap.
Yeah, for disambiguation, right, between the two.
I see. So you're saying when you're doing this not operation.
Right.
Okay. Yeah, good point. So beyond synonym resolution, I'm also interested in web mining techniques for a number of different applications. I'm particularly interested in language acquisition, but also I've talked a bit about web mining for improving NLP tools. And of course, NLP tools are involved in web mining. So I'd be interested in looking at trying to iterate that process and improving both. I'm also interested in trying to do web mining for actual AI applications, which tend to need more common sense information rather than the facts that we've been extracting. So can we extract things that would be useful to AI applications like actions and their effects? And then finally, there's another kind of data source very much like the web in that it's very large and unlabeled, and that is video. And I'd be interested in trying to port the kinds of principles that I've been talking about for web mining onto the world of video. So there are a number of people I've worked with throughout graduate school, and I especially like to acknowledge my advisor, Oren Etzioni. And I've referred to a bunch of different systems and papers throughout the talk. Here are the references for those. Thanks a lot. Yeah.
Could you comment on the time taken for a single query to get like synonyms, like for an object or for a relation? I mean, how much time does it take on an average?
I don't know on average. I know that clustering the set of 2 million extractions that I did for the experiments took about a half hour, and clustering the 100 million extractions took about 3 days.
Excuse me, you mentioned 2 million. You mean 2 million web pages or 2 million candidates?
2 million extractions.
Extractions.
Yeah.
Did you try to see how the size of the original data affects the quality?
How the size of the original data?
Yeah, if we take more data, will it be more reliable if we set, higher thresholds or something?
Oh, I see. So when I did the 100 million data set, I used the same settings as the 2 million data set. And it's a little bit too big to actually go through and label everything to see how correct or how accurate my system was on the data set. But just sort of by inspection, it didn't seem to do any better or worse. So I don't think it might be possible that using a different threshold would improve the precision, but it looks like it's roughly the same performance. Yeah.
How general do you think your techniques are? I mean, can you, what was it? The actual tuple extractor was, what was it called? Resolver?
Text runner.
Text runner. I mean, so do you think you could sort of plug in or use these techniques with other types of extractors as well? I mean, running off query logs or things like that?
So
they don't need to be tuples, right? I mean,
right, no, that's not, as long as there's some notion of a property, my technique should apply. There may need, as Lucy said, if properties are of different lengths, you may need to adapt the model to take that into account. But I think the model is general. Some of the parameters that I haven't talked about how to set those parameters will not port across different data sets. But basically what I've done to set those is take a development set and tune it. But yeah, the property is a very general model just because it's based on this very abstract notion of pulling balls out of an urn. And lots of different information extraction processes can be modeled by that. Yeah.
For the common nouns that are in your data set, a different way to measure recall would be to see whether they were found in the synsets in WordNet. Did you try that at all? Because, your description of how you calculate recall is somewhat biased by the data you have at hand.
Yeah. So I actually didn't do common nouns for this test, partly because they're tupulismus. So I wasn't able to get a good clustering for them. Basically, every cluster was incorrect in some sense. So I didn't compare to WordNet for this. I just used proper nouns and proper noun things and proper noun sequences.
Yeah, because I think
I'm sorry if that was confusing.
I knew that there was a limit that you chose things that had properties that occurred more than 25 times.
Yeah.
But you did make it clear that it was also.
Sorry. Yeah. I should say the text runner is targeted towards proper nouns, so it extracts more proper nouns on average. It also extracts common nouns, but it's sort of more biased towards extracting proper nouns.
So that explains why the string matching did as well as it did then.
Yeah. Uh-huh.
So I actually have two questions. One is, so I was noticing that at several points throughout the talk where you were running into problems was because you had these very low counts on relations and Like, for example, you only had like 5 properties in common between Mars and Red Planet and all that. And I wonder whether that's, the underlying extraction system is, presumably the reason for that is the underlying extraction system is very focused on high precision and low recall. So it almost belies that the assumption, you've made this point in your very first page, which was that the nice thing about the web is that it's large enough that you can use high precision, low recall technique. But what your work is actually showing is, in fact, it's not even big enough for that. Because if you have a high precision, low recall system and you run it over the entire web, you still end up with lots of stuff that has very little evidence for it. You have fairly common things, something in the news like Mars, for which you have only a handful of relations.
Right, but I'd still like to point out that the results from Resolver are, they're not perfect, but they're still doing a decent job of doing synonym resolution, even with that small number of shared properties.
No, this is actually a comment on the assumptions built into TextRunner rather than Resolver, which is to say that the assumption that you can actually get by with a very high precision and presumably very low recall system may not in fact be valid in all situations.
I would agree with that. At least in part, I think. So it's true that TextRunner is not going to extract nearly all the properties that can be found on the web, but also part of the reason for their sort of low number of shared properties is just that there may not be as many mentions of one of the strings as the other. So we saw, for instance, that Red Planet was only extracted 70 times as compared to Mars's 700 or so. So I agree. There's a problem of recall with TextRunner. You might also, so we ran TextRunner over around 150 million web pages. When we get to larger data sets, hopefully part of that will address the problem of recall.
The second point I want to make is, so you might want to take a look, I don't know if you're familiar with, so you've got Lin and Pentel up there, but Dekang Lin's earlier paper actually from ACL 1998, which is purely on similarity, is I think very similar to what you're doing. I mean, the main difference is that his relations come from his dependency parser, whereas your relations come from TextRunner, but the actual similarity computation, I think, is either the same or very similar.
From what I remember, he uses a mutual information-based statistic.
Well, Hindle, he references Hindle 1990, and Hindle uses a mutual information metric. But his is a little different. Well, anyway,
I'll take a look. Sure. Thanks. Other questions?
Thank you.